So now I want to teach you specifically about projectiles above the ground. And what that means is normally when you have projectile motion, we have questions that start at the origin there, 0, 0. So it starts from there. But now we're going to explore what happens if you throw an object off a cliff or a platform above the origin like that. And it poses some unique questions which we're going to go through later. Okay? So question 2 here, we're going to use the origin as a base of the cliff, and we're not going to care about air resistance, and we'll take gravity as 10 meters per second squared. And the cliff is 35 meters above the ground. The angle of projection is 45 degrees and velocity is 16. Now the point of this module here is to teach you specifically about when we have projectile motion above the ground. So when we do questions like 2A, where we want to derive the equation of the horizontal displacement, we're not going to go through all the steps just because it takes too long, but you know for yourself that in an exam, that's what you need to do, right? So firstly, the horizontal displacement equation, we can just use that there. And just substituting this equation, where V equals to 16 and 45 degrees is our angle, okay, we get gives us 8 square root 2, and that's because we have 16 times 1 on square root 2, which is square root 2, and then you just quickly rationalize that. So you get 16 square root 2 on 2, which cancels down to 8 square root 2, like that. So that is our horizontal displacement equation. Now, just going to emphasize again, we're just doing this because for the sake of time, we want to focus on some questions later on, but in an exam, you have to start off with acceleration and then integrate until you get that horizontal displacement equation. All right, what about the vertical displacement equation? So just using this down here, we're going to substitute in the various values. So we said gravity would be 10, so we substitute that in. Our velocity is 16, 45 degrees. And now this 35 comes from that 35 there, because it's 35 meters above the ground. So that's why we add 35 with our horizontal displacement. Okay, so now some simplification. Negative 10 divided by 2 gives us negative 5. Here we have 16 times 1 on square root 2, which was 8 square root 2t plus 35. So this is our equation for the vertical displacement. And just remember with that, if it's going up by 35, you add 35. If it was above the ground by 100, you add 100. So pretty simple to know what you need to add for that. All right. Now we've worked out the horizontal displacement equation and the vertical displacement equation. We're going to use both of those to work out the equation of the trajectory. So remember, the trajectory occurred when there was only x and y, so we need to eliminate t. And to do that, we're going to start off by using this equation here. All right. And all we've done is divided 8 square root 2 onto the other side, so we get t equals to x on 8 square root 2. And now we're going to use this equation, and all we're going to do is wherever there's t, I'm going to substitute in x on 8 square root 2. So here we have that equation, and wherever there's t, I've substituted in x on 8 square root 2. And t here, exactly the same thing. And just cancel that. There's really nothing else much you can cancel. So just a bit of working out. So that becomes negative 5x squared on 128 plus x just by itself plus 35. So this here is our equation of the trajectory, which all we need to do is eliminate t by rearranging our horizontal displacement equation and substituting that into our vertical displacement equation there. Great. Let's move on to this one, which is where we want to calculate the time the stone will take to land in the water. So think about that. That means the time the stone will take to land in the water, still occurs when y equals to 0. So it still occurs when the displacement equals to 0, okay? So that's not affected by the fact that it's thrown off a cliff. Now, that means we want to take this equation over here and make it equal to 0. But the only difference here is because we have that 35 there and it's not just 0, it means we can't factorize out the t like we normally would to work it out. So in this case, I want you to use a quadratic formula. All right, and remember, what was that? So that's going to be negative b plus or minus square root b squared minus 4ac on 2a. All right, and that's one big thing here that you see when we put that in. So negative b plus or minus b squared, so that was 128, minus 4 times a times c on 2 times a. And just put that into your calculator. Be a little bit careful. What I would do is work that out first, square root it, and then put it together, because otherwise just too many things going on. And then using that equation, we see that t can either equal to 1.75 or 4.01. Now, because of the nature of our diagram, you can see that negative 1.75 would be over here, which doesn't exist in projectile motion, and that makes sense because negative time doesn't exist in real life either. So that's why we take our 4.01 as the time of flight. So it actually takes 4.01 seconds for this stone to land in the water, right? So time of flight, even when we do have above the ground, it doesn't really change anything. It's still when y equals to 0, when it hits the ground. Okay, well, what about when we want to calculate the distance from the foot of the cliff? How are we going to do that? So when we normally just have a projectile, so if we were starting from here, right, we talk about the range of the horizontal motion, and that's very similar to when we want to calculate the distance from the foot of the cliff. Because looking at that diagram there, the distance from the foot of the cliff is given to us by that there, right? Okay, and all that is your horizontal displacement at the time that hits the water, which is your time of flight, which means all you need to do is use your horizontal displacement equation there, which is 8 square root 2t, substitute in the time of flight, like that, and work it out. And it just equals to 54.37 meters. So what you've worked out is that distance there is 54.37 meters, and it's similar to your range of your motion here. All right. So that's what I want you to think about when you see calculate the distance from the base of the cliff or base of the platform. Good. Now, calculating its maximum height. Do you think there's going to be a difference here because it's going off a cliff or not? Well, not really, because what you see is the maximum height still occurs when your displacement equals to 0. Sorry, your velocity equals to 0. So it still occurs here when your vertical velocity equals to 0, when it stops at the top. That's not going to be affected at all. So we're still working out that there, the maximum height of that, all right? Which means that we need to firstly find out our vertical velocity equation, and all you can do is have a look here, and that is our vertical displacement equation, and just differentiate that. So differentiating this, take the 2 down, that becomes negative 10t, this becomes 8 square root 2. So this is our vertical velocity, and make that equal to 0. And for this one, 8 square root 2 equals to, just move over the 10t, okay? Divide both sides by 10, and that's how you get, so remember here we have 8 square root 2 on 10, and that's how you get 4, just cancel down, 4 square root 2 on 5 as t. So remember, that was the time that you get the maximum. Yeah, so that's not your final answer, that's just the time that you get the maximum. To work out the actual maximum, we need to use our vertical displacement equation here and substitute in the time of 4 square root 2 on 5. Okay, so substituting in t squared for that, and t becomes that as well. And now with this, I think the best way is just put into a calculator. Don't need to do any more work than that. And we get 41.4 meters. So that there is 41.4. All right. Now, just be wary here that when we talk about the maximum height, it's maximum height of the projection. So naturally it would go down to the ground level. Okay. It has nothing to do with the starting level at all. It's still going down to that 0 level there. Good. So that's calculating the maximum height. And now we get to these questions which I was telling that occur only specifically when you have something that is above the ground. So here I'm going to work with you to find out the impact speed that the stone takes to land in the water. So what we want to work out is essentially the velocity as it lands in the water, and not the horizontal velocity, not the vertical velocity, but the velocity of the actual projectile motion object itself. So we want essentially that velocity, but over here. So what we want to find out is that velocity there. All right. Now, similarly to how with that velocity there, we could draw ourselves a right angle triangle, we can do exactly the same thing. So we can say that this here, okay, that's going to be our vertical velocity, right? Whereas that here is going to be our horizontal velocity. Now, it doesn't make a triangle quite yet, but if you take this here, okay, now this is exactly the same as that. So if you take that y to equal that, then you can see that we have this triangle here. Can you see how we have that triangle there? That's right angled, which is similar to the triangle we have there to work out the impact, so that velocity there, okay? Which means to work out that velocity, I need both my horizontal and my, good, vertical velocity. And let's work out our vertical velocity. So our vertical velocity there is given to us by this equation, which we worked out previously. Now the vertical velocity, remember how it changes throughout time? So the time here, it was 4.01. So just substitute that in. So the vertical velocity as a stone hits the water is -10 multiplied by 4.01, which is the time, plus this, which equals to approximately -28.79 meters per second. Now our horizontal velocity, we can just work out from differentiating our horizontal displacement, which was 8 square root 2t. So just differentiate that, you get 8 square root 2. So now it's just easy Pythagoras. So you know the impact speed will be the square root of that squared plus that squared, like that, okay? So your vertical and your horizontal velocity there. Now putting that into your calculator, you get that this v here, that velocity, is 30.93. So what that is the impact speed, so impact velocity of the stone as it lands in the water is 30.93 meters per second. All right. Now, just remember for this one, what we're doing is exactly as what we did right at the very start. We said that's our velocity, yeah? And we can divide that into vertical and horizontal velocity. And when we do that, we made this right angle triangle, exactly what we're doing here. That's our velocity there. We had our vertical and our horizontal. The only difference was I moved that over there, okay, to form a triangle. And then it was just simply some Pythagoras, wasn't it, to work out what the velocity was as a stone hit the water. Excellent. Okay, so this is another question which is unique to questions above the ground. And this is finding the impact angle that the stone takes to land in the water. So in the same way, we have our velocity, remember? There, okay? And there was our vertical velocity there, and there was our horizontal velocity there. And all I did was I transposed that to this side because I said it was exactly the same and made myself this triangle there. So we worked out already that this was 8 square root 2 and that was negative 28.79. So how am I going to work out this angle there? What we're going to do is just tan theta, right? So you just have opposite on adjacent. So in this case, it's just negative 28.79 on 8 square root 2, which equals to approximately negative 2.54, etc. But keep that value exact in your calculator. And then we do inverse tan of that value, which equals to approximately negative 86 degrees and 33 minutes. Now, negative is an interesting concept here because what I need you to think about is that there is a line here, okay? And anything that goes from here is positive. So this is your positive angle over here, whereas this over here is your negative angle. So anything going from there is your negative angle. So here, because it's negative 86 degrees and 33 minutes, it's going to be that angle there, which is 86 degrees and 33 minutes, okay? So just remember, negative on this side, positive on that side. Just commit that to memory, all right? And you know that this here, negative 86 degrees and 33 minutes, is the angle that of the impact as a stone hits the water. All right, so just remember for these ones, when you want to find out the impact angle and the velocity as a stone hits the water, we're not worrying about vertical, horizontal. What we're worrying about is that big V that I showed you before. Okay, so that's question 2 here, and I hope that it makes sense to you because I know it can be a bit difficult with above the ground questions, but just remember the differences were those last 2 questions there. All right, let's move on to question 3. So great work getting through question 2. There wasn't an easy question. Now, in question 3, we have this particle which is projected horizontally from the top of a cliff 20 meters above the water, and it's with a velocity of 30 meters per second, and we just assume that gravity is 10. Now, let's work out the equation of the horizontal displacement. Now remember, because it's just thrown like horizontally off the cliff, we just say that it's 0 degrees there. Good? And we just use this equation over here. All right. So velocity was 30, and our degrees we just worked out was 0 degrees. So cos 0 is just 1. So our horizontal displacement equation here is just 30t. Now, moving on to finding the vertical displacement. So in this case, I'm going to be working with this equation here. All right, and just substituting things in. So G was 10, 30, 0 degrees plus 20. Now, because I know that sine 0 degrees is 0, that means this whole thing essentially just becomes 0. So that's why you just get negative 5t squared plus 20. So that gives me the equation of the vertical displacement. Okay, so we're just using equations here because for the sake of time, I just want to show you something rather than how you would set it out in an exam. All right, now let's find the time taken to reach the water there. So this is when we want to consider, when is it going to reach the water? Well, that's going to be this point there, right? And that's going to be when y equals to 0. And that means all I need to do, take this equation here, yeah? and make it equal to 0. Pretty simple. And then I think to myself, what can I factorize out, make it easy? Well, you can divide everything by -5 quite easily, right? So dividing that by -5, I get t squared. Dividing this by -5, I get -4 equals to 0. And that equals to factorizing it. Easy factorization compared to the last factorization we did. T plus 2, t negative 2 equals to 0, like that. So that means t equals to -2 or 2. Time can't be negative, so that means the time taken to reach the water is 2 seconds. So it takes 2 seconds for that object to reach the water there, which is when y equals to 0. So remember how I said it didn't really matter if it was thrown off a cliff or not? For it to reach the ground or the water, whatever it is, it's still always y equals to 0 there. So the vertical displacement equals to 0. Good. Now, we want to find the horizontal distance travelled. So the horizontal distance travelled is going to be what? It's going to be this distance over here, right? So it's very like diagrammatic when you think about this. If you can think of it in a diagram, you can always imagine this. It's going to be that distance, which is given to us by this equation. Now, t is our variable, and we know that the time there is given to us by 2. So that means this is a simple question of just using this equation, which is x equals to 30, substituting in the time of flight, which is 2, and finding out that that is just 60 meters, right? Simple. So a lot of people just simply get confused because you're not used to it from starting above the ground. But if you just think about it in a diagram, the distance traveled is just from here to there. So exactly the same as the range of horizontal motion, which is given to you by the horizontal displacement equation and substituting in the time of flight.